All right, let's go ahead and get started. So I did get the exams graded, so I'll hand those back. Overall, I was really pleased with the grades, so I like them. And then there may be opportunity to like remake some credit if you did do poorly, but we can discuss that later and on an individual basis. I think there's still like 1 or 2 exams that need to be done in the test center. And if you haven't set that up ASAP. Oh no. Why? There we go. Uh-oh. All right. Any questions before we get started or anything? Yeah.
Is the lab we did last week going to be kind of the same as the lab we're doing on Thursday, or is it going to be over different material?
Let me.
Or Wednesday, sorry. What day is it?
So your lab this week is moles and chemical formulas.
Is that the one you handed out last week? Or is that?
We did reactions last week?
Yeah.
Oh, okay. Never mind.
Yeah, we did a bunch of baby reactions last week, and this week we'll be doing like determining formulas, which should match with our lesson. So let's start with chemical and physical changes. So we had said previously that physical changes, they do not alter the state of appearance, but are just physical changes. So that could be a state change, adding energy, you could be physically ripping something apart, you could be dissolving something. So again, just as long as you're not altering the appearance. Wow, my computer is having a hard time today. What is going on? And so meanwhile, so now we'll be shifting to chemical changes. And so chemical changes do alter the composition of matter. And so we're not destroying anything, right? We have the same number of atoms, and so they're merely just rearranging. And so this is different from like a nuclear reaction where the identity is changing, but when we're just talking about chemical changes, we're not changing the identity, so they're just being rearranged. And so you've probably seen that with things rusting. So you start with a nice nail, and then you leave it outside, and you get exposed to all the water, the oxygen, the elements, and then that starts forming iron oxide, and you can see it starts taking a new form with that oxygen getting intercalated then into the new structure. And then obviously that changes the properties of that nail, so it becomes weak as it turns into the iron oxide. And so then we want to be able to write and balance these chemical reactions. And you kind of got a taste of that last week at least. And so again, those reactions just involve rearrangement and exchange of atoms to produce new molecules. So we have reactants always goes on the left side, and we have an arrow. So right now we're just working with this one directional right arrow, which is just basically implying, it's going to go to completion, and everything will go from reactants to products. And then products are always on the right side. And so this is super important. And again, if you were a chemist, you'd probably do this every day, multiple times a day, setting up your reaction, whatever you're doing. If you're doing drug synthesis or catalyst synthesis, you're still going to be setting up what you're putting in and what you expect to make over and over again. And so a proper chemical equation should also state, so it states the quantities, and this is going to be in like a mole-mole ratio format. And the chemical identities, so of course that's just the formula. And so that's why it's really important that we know how to write our ionic formulas and our covalent formulas properly. So we want to write our proper formula and then their physical state. And so you have the little, either solid, liquid, gas. So gas is a little g, L if something is a liquid. And this would be like if your substance itself is a liquid, so you have like H2O, or an organic solvent would be a liquid. And then solid, of course, is S. And then you may also see this AQ, which means an aqueous solution. And you've worked with these, so, you know, like your copper chloride solution or copper nitrate, whatever, as long as it's in a little bit of water, that's considered an aqueous solution. And it usually has some molarity attached to it. And that's just a unit of concentration, which we'll cover later in the chapter, or in the course, I mean. And so again, we have our chemical equation, so it tells us what our reactants or products are. So again, we have to have our proper formula, either molecular or ionic. And it gives us a state. So this is really important if you were setting up a reaction in lab, right? You'd want to know what state does the reagent need to be in to add it successfully based upon your procedure. And then again, the relative number of reactants and products. And so this is really important. Just like you have a recipe, you have to have the right ratio of flour to eggs to sugar. If you want to make a cake or a cookie or whatever you want, they have different ratios. And then the other, of course, super important thing is we can use this to determine weights of the reactants used. And obviously, right, that's super important. You have to know how much do I need to measure to stick in my flask. And then you also want to know, well, how much product should I be isolating from my reaction? And this is really important as well. You know, if you were doing some sort of aqueous workup, you want to know, well, how much product should I roughly expect, so I know that, yeah, I probably extracted everything and I did a good job. And so these quantities then, so the amount of substance used and made in a reaction is related to all the amounts of substances. And so again, we usually balance it by the mole-mole ratio, but it does also follow the law of conservation of mass. So you could use mass balancing to solve it, but I don't want to get too much into it unless you're like doing it and you feel comfortable doing it, and then I'm more than happy to break down and explain this to you. But I think it's better if we kind of stick to the mole-mole ratio, balancing our equations by doing our atoms, and then we'll use what's called stoichiometry, which is really just a fancy word for saying we're going to figure out how much quantity we need and turn that into moles and go back and forth. And so again, this is super important, stoichiometry. And so here we have our reaction, and so now we have our little recipe. And we could either say this is for 1 atom, so we could take 1 atom of methane, react it with 2 atoms of oxygen, and this gives us 1 molecule of CO2 and 2 molecules of water. And then, so we can do some bookkeeping. So you want to just count out how many atoms do you have on the left side versus the right side. So we can just start. So we have 1 carbon, and then 4 hydrogens, and they already balanced it for us, so 2 times 2, so 4 oxygen. And then make sure that's true on the right side. So 1 carbon, 2, so 2 times 2, so 4 oxygen, and then 2 times 2, so 4 hydrogen. And so notice when they went to balance this equation and get the same number of atoms on each side, right, they just used the coefficients to balance it. And so that's what you would do too, right? You just start off with writing your proper formula. So there's the methane formula, right, O2. So don't forget your diatomics. And so that's where you want to highlight your diatomics. So anytime you see like nitrogen or hydrogen, you know, okay, I have to write N2 first, or H2. And then, of course, proper formula for CO2, proper formula for water, and then just, again, balance it with the coefficient. And so not only is this telling us the atoms in is, so the coefficients also specify the relative amount in each moles. So this means we also have 1 mole of methane plus 2 moles of O2 gives us 1 mole of CO2 and 2 moles of H2O. And then we could, of course, multiply it by any factor, scale it up or down, right? Just like you do with cookies. So you have a recipe for, 2 dozen cookies, but you're having all your friends over, so maybe you need 50 cookies or 100 cookies, and you can just scale up the recipe by however much you need. So same thing with this, right? If you want to scale it up times 10, then you're just saying, well, I know I need 10 moles of methane plus 20 moles of O2 to give me 10 moles of CO2 and 20 moles of H2O. So you can scale it up, scale it down, do 0.1 moles. Really doesn't matter. And so now if we look at this chemical reaction to tell us what it's saying. And so this is octane. So this is what's going on in your car. So you have octane, which is a liquid, is combusted. And so it's 2 moles of octane react with 25 moles of oxygen gas to give us 16 moles of CO2 and then 18 moles of water. And of course, you could also say that that's 2 molecules reacts with 25 molecules to form 16 molecules of carbon dioxide and 18 molecules of water.
So moles is kind of measurement of molecules.
Roughly. So we'll define, so 1 mole, because I think we're getting to this, is 6.022 times 10 to the 23rd, either atoms or molecules. But yeah, essentially, so you can relate it, right? It doesn't matter if we're looking at 1 atom or 1 mole, and then you can scale it half a mole, 0.1 mole, up and down, it doesn't matter. They'll just scale. All right, so let's see if we can relate it to food. And we'll practice with food. And then hopefully when we do chemistry, you'll feel comfortable. And so in this case, if you're trying to make a pizza, so of course the number of pizzas you can make depends on the amount of ingredients you use and what you have available. And so to make a pizza, they have 1 crust plus 5 ounces of tomato sauce plus 2 cups of cheese is equal to 1 pizza. And of course we can just express this in terms of a ratio. And then if we had 10 cups of cheese, you could set up a ratio or your stoichiometry. And so this is where your kind of dimensional analysis comes back to haunt you. And so we have, well, if we have 10 cups of cheese, and then this is now just your mole ratio for your conversion, essentially. So then you go back to your balanced equation, and you say, well, for every 2 cups of cheese, I can make 1 pizza. And then, of course, you can write this the other way, or 1 pizza is equal to 2 cups of cheese. So there's your conversion factor. And then now we have to set up our dimensional analysis. So if we're trying to get from cups of cheese to pizza, then we have 10 cups of cheese times our mole ratio, so we'd use our conversion factor with pizza on top, cups of cheese on bottom, so cups of cheese cancels, and then that gives us 5 pizzas. So let's do some pretend s'mores. And so our recipe for s'mores, so we have to start off with our recipe. So let's do, so we have 2 graham crackers. Plus, and we need 1 jumbo marshmallow. Plus, and then we need 3 pieces of chocolate. And that gives us 1 s'more. And so now the first type of question that we could ask so our class, at least normally, is 20 people. How many of each ingredient do I need? So take a minute or two, see if you can figure this out. So how do we do this? So do we get an answer?
40, 20, 60.
So 40, 20, 60, exactly. So we just had to take our equation. So assuming everyone gets 1 s'more, so multiply that by 20. So that gives you 40 graham crackers, 20 marshmallows, plus 60 chocolates, give you 20 s'mores. Right? That's not too bad. So now let's try the other type of question you might see. So if I have 77 graham crackers and excess of marshmallows and chocolates, how many s'mores can I make? I can scroll up to the original equation. So did we get an answer?
38?
38.5. So that sounds good. And let's just go over what you did, because these numbers may seem simple, but it's good to practice. So 77 graham crackers, and I'm just going to be really explicit. And then we want to get our ratio, so we want to get to how many s'mores. And so you go back to your equation. So I have 2 grams for every 1 s'more. Bless you. So 2 graham crackers for every 1 s'more. You can write that the other way around. And then you just plug in. So I want graham crackers to cancel. Put 1 s'more on top. And I trust y'all on the math. So 38.5 s'mores, or 38 total. So let's try a very similar problem to this one, but these are technically called limiting reagent questions. And so we'll give you kind of 2 amounts of each, and then what you'll have to do is kind of figure out, well, how many s'mores can I make from one, how many from the other, and then which one will run out first. And so let's see what I mean by that. So if I have 321 chocolate pieces and 178 graham crackers, and let's just put excess marshmallows, how many s'mores? So I won't spoil the answer quite yet, but should be setting up some sort of ratio. So you have to do it twice essentially. So first you can compare, well, how many s'mores can I make from these chocolate pieces? And again, these numbers seem simple, but I'm still going to set it up. So we have our 3 to 1. So 3 chocolates gives me 1 s'more. And versus my graham crackers, so 178 graham crackers with my ratio. So again, s'more on top, 2 graham crackers on bottom. And so how many s'mores could we make from this 321 chocolate pieces? What did you say? 107. So what other people got? Just looking for a nod. Oh. So 107 s'mores. And then how many could we make from the 178 graham crackers? 89. And so this would be called our limiting reagent then, our graham cracker. So that calculation told us, okay, our graham crackers are going to run out first. And so that is going to be our limiting reagent, and we can only make 89 s'mores. All right, that's really good. I'm going to make a new page. So now let's kind of look at the next type of problem. So far, they've been kind of easy, but we've been in what's called mole space, right? So we're just looking at moles of everything. But that's not normally how we do things as chemists. And so let's set up our equation again. So 2 graham crackers plus 1 marshmallow plus 3 chocolates gives us 1 s'more. And so you know for chemicals, right, we have to add up all the atoms to get our molecular weight. So let's just give y'all some molecular weights. So the molecular weight of a graham cracker, so 1 mole of graham cracker is 55 grams per mole. So a marshmallow is 70 grams per mole, and 1 chocolate is 15 grams per mole. And so see if you can figure this out so by mass balancing. So what is then the mass of 1 s'more? All right, do we get an answer? 225? So 225 grams per mole. So that one, you just had to add up, so 2 graham crackers, so 2 times 55 plus 70 plus 15 times 3. And so if you think back to the experiment from last week, when we burned like the magnesium plus oxygen, that would be a really easy one to kind of mass balance as well. So you had magnesium plus oxygen, give you magnesium oxide. And so you could just take the mass, or figure out really the mass of oxygen added from your mass of magnesium oxide in the end. And so now, let's get into the other types of questions you would be asked. And so now let's say, if I have 777 grams of graham crackers, how many s'mores? And so I'll just set up what you should be doing. So start with your grams, 777 grams of graham cracker. And then the next step, you're going to be converting grams to moles. And I always say moles is like your safe space with these types of problems. If you can get back to moles, you can get back to the mole-mole ratio, go back to your original stoichiometry equation. So that's a really good place to be. And so we just need to use our conversion factor, so our molecular weight. And again, don't let it scare you on an exam when you have to calculate your own molecular weight. It's the same process. So now we put, 1 graham cracker, 1 mole of graham cracker is equal to 55 grams. So then we go from grams of graham crackers to moles of graham crackers. And then once we're at moles, we can go back to everything we were doing previously, so just comparing our ratio. So then 2 graham crackers gives us 1 s'more. So then 2 graham crackers, 1 s'more. So that my moles of graham crackers cancels. And so what did people get for how many s'mores we can make? 7. Is what other people got? I see some nods. I can punch it in as well. So divided by 55, divided by 2, so 7. And so, of course, we can also have the limiting reagent type problems. And so now a limiting reagent problem would look like if I have 420 grams of marshmallows and 334 grams of chocolates. How many s'mores? So remember, you'll have to do the problem twice essentially, so seeing which one runs out first. I'll give everyone a few minutes to at least get started. We get an answer. So I assume we have to convert some marshmallows to moles of marshmallows. So 1 mole of marshmallow is 70 grams. And then from here we can do our mole-mole ratio. So 1 marshmallow to 1 s'more. So how many s'mores could we make from our 420 grams of marshmallows? 6. So 6 s'mores. Then our last one, so 334 grams of chocolate. Oops. Convert that to moles. Then do your mole-mole ratio. Oops, I wrote the wrong thing here. So 1 s'more, 3 chocolates. And so how many s'mores do we get from our chocolate? So 7 s'mores. And so which one's our limiting reagent then? The marshmallows. So then we can only make 6 s'mores. So this would be our limiting reagent then. And then 6 s'mores can be made. I think that's basically all the types of problems. The other type of problem that we'll see, and we'll get to it, is this percent yield. And so this could be worded in a bunch of different ways. But basically, so you're with stoichiometry, right, this is saying how many I can make, under ideal conditions. And so same thing in lab, right? You expect that you get X number of grams if everything goes well. And we all know that, of course, in lab, you don't get 100% transfer rate, or you may even spill something and then you really lost some due to error. And so that's where your percent yield comes in. And so we'll just do a simplified problem for now. But let's just say, so we expected to make 60 s'mores. However, we got too hungry and only made 56 s'mores. And so then what is the percent yield? And so all percent yield is formula-wise, it's actual over theoretical. So you would take your theoretical yield. Again, usually you would calculate it from your stoichiometry equation. That's what you're doing. That's what you're expecting to get. But then whatever you get in lab, of course, is what happens in lab. Then times it by 100 to get a percent. So in our case, it would just be 56 divided by 60 times 100. So I'll let you all punch that in and tell me what number that is. $93. So 93% yield. And so in organic chemistry, if you're again, drug synthesis, you want to have generally 90 plus yield. That's good. Of course, the closer you get to 100, the better. And just as an aside, so you have to think about your yield at each step. And let's say you had, a 7-step synthesis. And this would be a really short synthesis. But if you're getting, a 90% yield, so that's 90 times 0.9 times 0.9. So that's 0.9 to the 7th power. So 0.9 to the power of 7. And so even with 90% yield, you would only have an overall yield of 47% by the time you got done with this 7-step synthesis. And so that's why, and again, this is just an aside, but that's why you want really high yields, especially if you're in industry. You want to be getting as close as you can as possible, since obviously you lose stuff along the way. And with organic chemistry, they can easily have 20-step synthesis plus for some of those natural product synthesis, organic compounds. And I've heard some horror stories of people losing MIGs of their product in the drain pipe, and then they have to do drain pipe extractions, or there's these things called rotovaps where they dry off your product, but they're held on by a little bulb. Here, let me find a picture of a rotovap. So this is a rotovap, and so your compound would be in a bulb here or something. But what can happen is if you're not careful, that little bulb pops off and your whole product ends up in this water bath here, and you do not want to do a water bath extraction. But sometimes you got to, if you're on step 20, you don't want to redo your whole synthesis. So I've heard horror stories of grad students doing water bath extractions and all sorts of things to recover product. All right, so now we feel ready to do it with chemicals, right? We're going to do it 100%. No, seriously though, if you could do this, it's the same process. So just slow yourself down. Don't let the chemicals scare you. I swear that's what happens. So I will print this out for you while you take your quiz. But this is just a really handy dandy chart to kind of help you navigate. So I'll at least explain it. And so again, moles is in the middle of kind of our safe space. And then so we have, this says use stoichiometry from chemical equations. So all that's saying, right, is you can compare your mole-mole ratios from your equation, from your little recipe, to give you moles of reactants or products. Then we mention Avogadro's number, which we'll get to. So if it gives you like number of particles, you can divide by Avogadro's number or multiply. So I like this chart because it tells you. And again, it's all dimensional analysis, but it's always good to have a refresher. So if you have so many number of particles, divide by Avogadro's number, that gives you back to moles. If you were asked how many atoms of this, how many particles, you multiply by Avogadro's number to get you particles. And then this is probably the one you'll be doing the most. So from mass to moles and back and forth. So you can see if we start with mass, we just divide by the molecular weight to get moles. We saw that with our dimensional analysis. And then of course, if you need to go from moles to mass, then you just multiply by the molecular weight. And then this will come up probably later, but not in this chapter, but we'll get to kind of volume and density, but you could use that as well. So of course, density equals mass over volume. So if it does come up, so multiply by density to get grams. So if you're volume, get to grams, or if you're grams, divide by density, get volume. Of course, we have the triangle trick to help us. Make sure I didn't skip anything. All right, so now we're ready for chemicals and moles. So now we're back to our combustion reaction. So back to 2 moles of octane plus 25 moles of oxygen gives us 16 moles of carbon dioxide and 18 moles of water. And so, of course, the same way that we use the ratio from the pizza or all the s'mores, that's the same thing we're going to be doing here. And so now the numbers are a little nastier, but again, don't let that scare you. So we have a 2 to 16 ratio moles of octane to CO2. We could relate it to our O2, so it doesn't matter what we relate it to, right? So we could do 2 to 25, 2 to 16, 2 to 18, whatever we're interested in. And so all this is saying is, right, we can do product to product. It doesn't matter. It's just all ratios, all conversions. And so we won't reveal the answer yet. So see if you can go through this. So how many moles of CO2 are formed then if 22 moles of octane are combusted? And so they gave us a balanced equation. So can we figure it out from here? did we get an answer yet? Let's see, one nod at least. And so let's look at how they set it up. So I will say there's another way to do it, but just sticking with the dimensional analysis method. So we started with 22 moles of our octane, and then we have, right, our mole-mole ratio. And so just setting up our dimensional analysis. So if we're interested, so they were asking about CO2. So that means I'm going to compare my CO2 to octane ratio. And then we'll just cancel out moles of octane using our conversion factor. And then, so if we do the math, we should get 176 moles of CO2. Is that what I see? It's one nod. Now I will say, if you like proportions, you can also set up a proportion. So you could go, well, for every 2 moles of C8H18, you have 16 moles of CO2. So then if I have 22 moles of C8H18, that gives me X for CO2. And let me just plug it in so y'all will believe me. So 22 times 16 divided by 2, and so that also gives you 176. So if you like proportions, feel free to use them. They're handy, but I'll probably just stick to dimensional analysis and setting it up in this way so you get used to it with all the conversion factors and everything. So any questions about this one, by the way? So hopefully we feel comfortable. So again, just always take it back to the s'mores if you need to, or food, just something concrete, because you can think about, you know, cooking and a recipe and scaling that up and down. This is the same thing. So if you can cook, you can do chemistry yet.
Oh, is that why you put the original as 22.0? So that's 3 statements because our IH came out as 176. If it had just been 22 moles, we have to round that last.
Yeah, so then, yep.
Okay.
Good question and catch there. So 180 moles if it was 22. And so now this is just saying what we practice with the graham crackers. So usually you'll go mole to mass or mass to mass. And so we might have to. And all this is saying is if you have a mass of something, we just want to get it to moles so we can compare the mole-mole ratio. So that is the key. So we need mole-mole ratio to compare. And again, you could do mass balancing, but it's a little different that, again, I don't want to talk about it because I don't want to confuse people unless you really want to use it. But I'm more than happy to go over mass balancing, probably like individually or in recitation if people really want it. But from my experience, most people don't mass balance. I think it's more confusing. So we want to get to that mole-mole ratio. All right, so let's take a look at this and see if we can approach it. So now we have our little recipe, and now it's saying we'll determine the mass of CO2 produced when 3.6 times 10 to the 15 grams of octane is burned in excess oxygen. So at least we don't have to worry about the oxygen, but then we just need to convert grams to moles, mole-mole ratio, and so highlight which ones you're interested in. So we're comparing octane, and then we want CO2. And so now I'll give you a couple of minutes. So can you figure that out? And ask your neighbor, ask your friend, look back at your s'mores. How do we do it? dots, and we start going over. So we started with 3.6 times 10 to the 15 grams of C8H18. And then what did we need after this?
Grams of CO2 to grams of C8H18.
So it seems like we need to go from mass into moles, right? Because we eventually need to get to grams of CO2 like you were saying, but we need to compare their ratio. And so they didn't give us the molecular weight, so we're going to have to do some work. So what's our molecular weight of octane? So something like 8 times 12.011 plus 18 times 1.008. And again, your numbers could vary. So do we get like 114 for the molecular weight or so? I see one nod. So now we have 114.232 grams per mole. Again, it's fine if your number's a little different from mine with rounding. And so now we set up, so I want moles of octane. So I put moles on top, whatever your mass is, so 114.232 on bottom. Then from there, so this gives us moles of octane. So then we have to use our ratio. And so if I want CO2, which one goes on top? So CO2, so 16 moles of CO2 are produced for every 2 moles of octane. And remember, this is straight from our formula, so we can go back 2 to 16. That's where we pulled it from. And then the last step is then we need to figure out, so that gives us moles of CO2, so that's good. But then that last part, it was asking for mass. So what's our molecular weight of CO2? Do we get 44 grams per mole for carbon dioxide's molecular weight? Sweet. See some nods. So 44 grams per mole. And so that's the last part. So 44 grams for every 1 mole of CO2. So now we can plug this whole shebang in our calculator. So 3.6 times 10 to the 15 divided by my molecular weight. And so that's moles of octane. Now I'm going to multiply it by 16 divided by 2. So now we have moles of CO2. And now multiply it by the mass, so 44. And so is this what everyone got for their final answer? I could have plugged something in wrong too. So I see one nod at least, looking for other. Thumbs up, thumbs down. What about this side of the room? Can we get it, not get it? No? What went wrong, or did I do something wrong, or? What are we thinking?
Can you explain
like where I got the 114. So the 114 we had to get just by adding up the C8H18 molecular weight. Because unlike the s'mores example, right, I just gave you the molecular weights, but they don't normally do that, so they're kind of mean. And so we just had to add up and find our molecular weight. So it was just 8 times 12 plus 18 roughly. So that gives you about 114. What you could also do, and this is more of like a cheat, but I don't mind if you do it just while you're like practicing. So like most chemists, they don't add up just the numbers to get to their molecular weight. There are programs that do it for you and make sure that you do it really accurately. So you can always check online, or if you were adding a reagent, right, you would refer to the bottle, and then the bottle would tell you how much it weighs. And so that's just another thing you can do. And so I know this is octane. It has the right formula, C8H18, and you can just at least double check yourself that, okay, I have the right molecular weight. But then from there, and you can also orient yourself on this. So Nicole, like this is a good way to help you. So you have like mass here, right? So it gave it to you in mass. And then you want to get to moles, though, so you always want to get to moles. And then your little chart tells you, so divide by molecular weight to get moles. And so we go back, okay, that's all we're doing here then, is dividing by our molecular weight. And so this gives us moles of octane. And then from there we can go to our ratio. And again, this is just from balanced equation. So you just look at your balanced equation, find whatever you're interested in, write your ratio, then moles of octane goes on bottom so that they cancel, giving me moles of CO2, and then from moles of CO2, mass. Does that make sense?
A little bit.
Yeah, it's a lot of steps, but just take it back to the s'mores.
Practice.
Yeah, it's a ton of practice. So I think we have time for at least one more practice. So magnesium hydroxide is the active ingredient in milk of magnesia, and it neutralizes stomach acid. And so the reaction is given here. So magnesium hydroxide plus 2 moles of hydrochloric acid gives you 2 moles of water and magnesium chloride. And so it asks what mass of HCl in grams is neutralized by a dose of milk of magnesia that contains 3.26 grams. Yeah.
So once you have a mass of HCl2, right, which is HCl, do you times that by 2 because there's 2 moles?
No, because the ratio only comes into play when you're like going back and forth between like, well, in this case, magnesium hydroxide to HCl, right? Because they're in a 1:2 ratio. And so you use a ratio to go from, well, you'll go from grams to moles, and then you'll use a ratio to go to moles of HCl, but then you're done with that. So you don't need to look at the 2 anymore. So take a few minutes, see if you can get started on this, and we'll go over it. So let's at least start by getting the molecular weights that we need. So what's the molecular weight of magnesium hydroxide? When people get, do you have an answer?
Yeah, I'm pretty sure.
For the mass of magnesium hydroxide?
Oh.
Let's start with that at least.
Just the mass of magnesium.
Hydroxide, yeah, if you have that handy.
58.319.
So that sounds good. And then HCl, what's its mass? 36.461. And that's all the ones we need. And so let's just start with our dimensional analysis. So start with what we know, 3.26 grams of magnesium hydroxide. And then we have our dimensional analysis. So we know, so 1 mole is 58.319 grams. Again, look back at your chart. Okay, we have mass. I need to get to moles. Divide by molecular weight. Okay, divide by molecular weight. That makes sense. So now we're at moles of magnesium hydroxide. And then we look at our formula now. So what's the ratio of magnesium hydroxide to hydrochloric acid? 1 to 2. And so I want HCl on top, since that's what we're looking for. And then we just solve for magnesium hydroxide. So I need that to cancel. So that's, again, where our stoichiometry comes into play. And so now we're at moles of HCl. And it asks for our answer in grams, though. So now we just have to take that last step. So this is grams per mole. So that means 1 mole. So moles will cancel. 36.461 grams on top. And so now we have to punch this whole thing in. So 3.26 divided by my molecular weight. And so now I'm at moles of magnesium hydroxide. Now we're going to multiply it by 2 from our ratio. So times 2. And then the last part times 36.416, or 461, sorry. And so did everyone get 4 grams about? I see one nod. And if we didn't get there, do we know why? Do we figure out how to get there?
Maybe a stupid question, but I'm just a little lost on where you're getting the molecular weight from.
So remember, we have to, it's all from the periodic table.
Oh, okay. The 24.305 for magnesium.
Yeah, sorry, I can pull up. I knew I should have put a periodic table.
That makes more sense.
Yeah, so you just have to add up. And then so magnesium hydroxide, you have like 15.999 for the oxygen plus your hydrogen, and then times 2 for 2 hydroxides plus the magnesium, so 24.305.
That makes more sense. Okay, thank you.
Yeah, so that's where things start to get tedious with these problems. So you're already seeing that, right? There's a ton of little places, so you have to get the mass of each of these potentially. But again, just add them all up. Don't worry about the coefficient when you're just trying to find the mass either, so just find the mass. And then you're just always trying to get to moles. So again, the grams makes it sound really confusing, but we're just going grams to moles. then mole-mole ratio to compare from our formula, and then back to mass. It's a little early, but it's all that I wanted to say for now. So Wednesday, we'll go over types of reactions, so like you did in lab, so we'll go over that, and then we'll just keep practicing this more and more, because it's a lot of practice. But let's go ahead, let's take a 10-minute break, and then we do have a quiz over Chapter 4 material, so before the exam, so it shouldn't be too hard. So we'll do that after, and then of course we'll do questions like we usually do. So take your 10-minute break. Then we'll do our quiz. And while you're doing your quiz, I'll hand back your exam. Oh, yeah, I will take it. Sorry, I'm behind on grading. So. And then I'm going to go print out some mole highways too while y'all take your 10-minute.
I did it all the night before.
You're like, I'll take it.
Yeah, like, as long as you have the equation, you could just plug in your own numbers, that'd be fine. Wanted to step back, so that's why.
I always do really good following along until like the end when she starts putting the numbers and not saying where they're coming from. It's raining numbers again.
On my last one, I didn't get the molecular weight of HCl, and I had 58.3 on mine at the top. So one that came out a little low. But I was happy when I got 58.3 on that correct.
biomes?
No, because that's,
Yeah, I don't know if you were gonna.
so like, oh, grade, like, third.
Oh, nervous.
Yeah. I mean, I wasn't that worried about it, because I like,
I kind of breathed.
I felt like,
Yeah. I felt comfortable with my mouth actually, but you know,
format.
like,
Ugly?
you know, there's always. Dude. My teacher sucks so much that 2 days ago when I found that she's like, that's pretty good.
For real?
Yeah, my teacher fucking sucks. Dude, she's so bad. Like, a sub came in and taught better than someone her. It was so sad.
For real.
I was about to contact her, so like, transfer up to like, head rock campus just to get her on class.
Not teach. Damn.
So many kids in our classroom. We're paying so much.
No, it sucks though. One of my buddies went to RCC's like 1 grants past because they don't offer the academic classes.
They don't?
I don't think they do. So it's the like what's called grants fest. Yeah, I asked him too because like that's like already the health
The health
building too.
department,
Yeah.
yeah.
And he's like, no, I have to go to grants fest. And I was like, yeah, that sucks.
We need to figure out transfer thing. Because right now it's basically in the transfer to OIG for
Oh. Yeah, we have to take that MIT 101 class.
in my
I think it's called MIT. Yeah, MIT 101. But it's RCC does offer it, but we take our first year. So I'm gonna take it during summer term online. That's what I'm gonna do. I wrote down everything. I was like, all the stuff that I need to do. Well, let's get just like accent. Good skill, I know. Yeah. You have to take summer term. That's so heavy. I don't want to do that. Yeah. I want to have to, I want to have some,
Yeah, I was really honestly about it. One's like, what? Yeah, do it.
and that's why I wanted to join the army just to finish school here. Because they also want to finish faster than the
Oh, yeah.
you know?
So then you would branch off from military.
Yeah. See what we got. Yeah, I think we just sign on boys, you know? So it's like, what do we got?
Most people's. You're gonna go and tap.
For real. Because I think their one is like up to like 50,000 for me. But yeah, but my paycheck and it was only like 11, but still not bad, you know? But considering and like only something like 70% of people are like actually doing the army. And then like out of those, or out of the remaining like 30%, I think like they're not qualifiable for other things for some reason too. Master exams and stuff like that. And only like 8% are able, you know, from people from ages 18 to 23 are able to join. So I was like, dude, come on, like you should up your prices, you know, up the bonus a little bit.
Yeah, you gotta really make.
Yeah, for real. That's what I'm thinking. Maybe joining the Air Force first, you know.
I kind of want to
The
do it.
Air Force. That's what they call it.
Oh, yeah, he thinks all day.
Yeah. Because they, like, they're bandits on them. Yeah.
Maybe.
For real. That's my second choice. So. Let's see what we do.
I was thinking about that.
Wait. Assignment, policy project.
the printer ate everything, so I don't have mold copies still. But luckily, I printed out your quiz in advance. All right, so I will hand out the quiz. And then, as usual, don't forget your muddiest point for a bonus. Even if you don't have a muddiest point, just you can always let me know how things are going. And I'll try run and babysit the copy machine. Yeah, I just didn't print it out yet.
Is it cool if I, I'll probably just print it off next time?
Yeah,
Because it's on Blackboard, isn't it?
yeah.
Yeah, I'll just print it out.
Okay, and then I will probably try to send their test over today. I should
Okay.
have enough time to test them time.
Okay, cool.
Alright.
Do I have to reach out?
No,
Before
you
the-
just show up.
I just show up.
Yeah,
And you said weekdays from like 8 to 4.
yeah, 8:30 to 4, I believe. I just don't remember, it's Monday through Thursday or Monday through Friday. I'll have to look at the website
And
again.
I can look it up too.
Yeah,
so- Cool, thank you.
sweet. Thank you. And then I can try to print out some homework copies, but the copier is having serious issues, so I don't know if I'll get them out today, but I will have them for you by Wednesday then. So I might try to sneak off and try to do a sneeze copier. forget, homework if you want. Homework if you want.
Why didn't we times it by 2? Because there's a 2 there.
So the 2 is just for like the mole ratio parts, but you wouldn't want to do that because then you'd be like doubling your mass.
Oh, okay.
Yeah,
So it's only the subscripts that you multiply, not the
Yeah.
coefficient. Okay.
yeah. if you want it.
Question. So on the lab, I can't figure out if this is combustion or double replacement.
So the first one's combustion, yeah.
Oh, it is combustion?
Yeah, so anytime you see the water, oxygen gives you CO2 plus water, it's always combustion.
Okay, thank you.
Are you in your office tomorrow, like after 11?
Want to do my office? So I'm trying to think of my schedule. I have class 10:30 to like 11:20, so then I'd be in the office like around 11:20. Sweet. Thank you.
I used to use a rotovent at work a lot.
Oh, nice.
Trying to get the ethanol back into some crude oil.
Yeah. Fun stuff, huh?
Except when like you have a leak in your system and you're trying to figure out where it is.
Yeah, that's never fun. All right. See ya.
is that all they're wanting?
Yeah, except, so, because the proper formula for magnesium oxide is just MgO, and then you would use the coefficient in front to balance it out.
Oh, in front of the whole thing? not-
Yeah,
Okay, got it.
yeah, because you gotta keep the MgO proper and then just put whatever coefficient.
Because it's all one molecule.
Yeah, exactly.
Okay, thank you.
Yeah.
It's two in the wrong spot.
Yeah. This is the part of the quarter, it's like chemistry is cumulative by nature. You probably want to start with like elements that are in most of them, so like I would do oxygen last.
So you start, okay.
Yeah, since like oxygen's by itself, like nitrogen's by itself, so do that last, like do iron last.
Okay. And is it okay to put one there?
Yeah.
Okay.
Yeah, if there's nothing, then it's just an implied one, but yeah, it's best to put one, just in case if you were to ever get like a multiple choice question, it would be like, what's the sum of the coefficients? So, you know, 1 + 1 + 1, you don't want to forget. But yeah, it's a lot of just guess and check and practice.
Yeah. Yeah, that's it. I think I did these in the wrong, I did F first.
Yeah, it doesn't matter too much as long as you get the right answer. So, I mean, that looks right, yeah.
Really?
Yeah, because 2 irons, 6 oxygen, 6 oxygen, 3 carbon, 3 carbon.
Oh, wait, why did I write that?
I think you just have 2 carbons here for some reason. But
Yeah. Cause I kept like doing different things and I always like had like more on this side than this on the other part. But I just ruined it for you.
Yeah, and this one's kind of tricky since you have like the P2O5 becoming something else. But, because otherwise I would say like in this case, like you have nitrate and nitrate, so you can try to balance it together. So you have like a 2 nitrate, so I would
Yeah.
start by putting like a 2 there.
Okay.
But
That helps a lot. Thank you.
is everyone done with their quizzes or just checking? I mean, probably just guess and check, which I know is not,
That works, okay.
yeah, because you could try to maybe start with like the hydrogen, since you have like even and odd,
Yeah,
and then you could do a 3 and 2 and just see like where that fits you.
okay, got it.
See ya.
So for the homework, is it also on Blackboard?
Yeah, I printed it out there.
Oh.
I managed to get the copy going. Yeah. Like everyone rocking the sweaters. Yeah. Yeah, yours is really nice, Alessandra.
You got like pulled out of nowhere.
Yeah.
It's like, oh.
We're getting like cold mornings and like hot afternoons, and now all of a sudden just like always cold.
Yeah. I'm not like a huge fan of the cold, so I hope I don't get shut down back.
I know.
Bye, thank you.
Yeah. Yeah, when I spent a year in Washington, I was like miserable. That's how cold it was.
Yeah, it is cold there. I guess I like Oregon because it has different seasons more so I feel like than like a lot of other places. It's kind of, I don't know, but it's also, it's hard to kind of figure out what weather to be like too in Oregon. So it always changes, it seems like.
Yeah.
I don't know.
And I hope it kind of warms up again.
I know.
But I guess it is late October, so.
Yeah. It's like summer, springtime more so.
Yeah.
Weather. I like both of them. I mean, the rain is nice as long as you're like not in it.
Yeah,
Just
exactly.
like looking at it, the kind of the vibe you get, but not the actual like.
Yeah, I totally get that. I love being inside with like a warm cup of coffee.
I know, right?
What? I'm supposed to do stuff? Be productive stuff?
I know. It just makes you want to sleep more.
Yeah, and then, oh my gosh, it's been getting dark too.
Oh, I know, right?
Like it was 8.
Or
and
is
then-
it 8? Yeah. Something like.
Yeah, I don't know when the sun rises, but it was like 8 o'clock and it still looked dark in my house.
Oh, really? Yeah.
So-
What kind of stuff do you cover in like Earth Club?
We actually are going on a hike this Saturday, which could be fun because it's gonna be, we're meeting in like Williams, but then it'll be at like the Marble Jones Quarry or something. And this guy, his name is Chaz Rogers. He used to teach the geology here. I think he still might as like an adjunct.